Hello and welcome everyone to this overview on digital core analysis with GeoDict 2023. My name is Christian Hinz and I am the business manager for digital rock physics at Math2Market. Until today, I have 9 years of experience with digital core analysis, both from the academic perspective and from my work at Math2Market, where I started in 2019. I've got specific expertise in the assessment of transport properties from 3D images of digital rocks, with a focus on water-rock interactions during my doctoral studies at the University of Mainz. This talk is going to start with an overview on digital rock physics, or DRP in short. So, what's DRP? Why are we doing this? What's the advantage of GeoDict in general? And of GeoDict 2023? So these are the questions that I'm going to tackle in the next couple of minutes. The need for a DRP workflow resides in the exploration of oil and gas reservoirs. The goal of core analysis in general is an improved understanding of reservoir properties as a solid foundation for decision-making at the management level, such as an optimized extraction of hydrocarbon resources. Therefore, the very basic requirement is the availability of representative rock samples, so drilled cores or at least rock cuttings of the geologic underground formations. Prepared rock samples may be measured via 3D imaging devices such as high-resolution microscopy to obtain a 3D gray value image. With such a reconstructed image scan, GeoDict may perform a digital core analysis. All the steps from image processing, segmentation and characterization, and the prediction of pore-scale rock properties. GeoDict results are then fed into reservoir simulators for kilometer-scale simulations. So digital core analysis provides a better understanding of reservoir properties. It thus contributes significantly to maximize the value of oil and gas reservoirs. The DRP workflow digitalizes special core analysis, and it saves time and costs compared to conventional skull lab work. But what's the specific advantage of GeoDict for this workflow? So first, GeoDict is the all-in-one solution for digital core analysis. You perform your entire workflow in our software suite. Second, GeoDict results are reproducible and numerically accurate. They are reliable and very efficient. GeoDict supports direct numerical simulations on 3D images beyond 2000 cubic voxels. And as a third point here, automation in GeoDict is fairly simple. You can automate any GeoDict workflow via our Python interface and thus increase your team's productivity. Depending on your needs, you can even push your GeoDict setup to cloud computing and obtain digital core analysis results as fast as technically possible, no matter how many samples you have. To provide you with a reference, here are some selected GeoDict users from the oil and gas industry and academia. And of course, there are many more clients, especially those for which we may not show the logo at this point in time. But we also have large companies in other business areas, some of which are shown here in the second list. And indeed, we have a continuously growing number of GeoDict users and many well-known names amongst them. Let's dive deeper into technical features for the most prominent GeoDict capabilities for digital rocks. I will start off with 3D image processing and segmentation. So the typical GeoDict workflow begins with the import of gray value data measured by a 3D imaging technique, such as a high-resolution micro-CT device. Imported data may be processed regarding image operations and image filters, such as non-local means filter or a ring artifact removal. Segmentation is about generating a voxel grid geometry with defined material features, either just a pore solid distribution or specific fluids and minerals. GeoDict offers various methods, from automated gray value throttling to AI segmentation methods. Geometric characterization is a basic step and includes pore space analysis and pore size distributions, amongst others. GeoDict also identifies and separates individual pores and grains as well as fractures. And on top we offer a fundamental quality check, especially for segmented sandstones. Any digital rock physics workflow includes the prediction of the absolute permeability. Therefore, typically the Stokes equation is solved, although we offer more solvers for specific setups. With this set of different solver options, upscaling workflows from micron to whole core scale may be realized in GeoDict. Our flow solvers offer an efficient and robust implementation that's applicable for large domain sizes, even beyond 4,000 cubic voxels. So here we see an animation of a primary drainage computed in GeoDict. So oil invades and displaces the formation water. For modeling two-phase flow, we apply the dynamic pore morphology method for direct numerical simulations. So we use a morphological method that's running on the voxel grid, without any geometrical simplifications. In GeoDict you may run MICP setups as well as combinations of drainage and imbibition in order to compute an entire hysteresis cycle. And GeoDict considers mixed wettability setups as well. This animation highlights computed velocities of water at an intermediate oil-water saturation of the aforementioned primary drainage. The velocities in this and further animations increase from blue to red color. GeoDict is capable of computing the relative permeability on basis of a set of two-phase fluid distributions. And as a result, the combined relative permeability curve is generated for the digital rock at desired wettability. GeoDict solvers also compute electrical properties. Amongst these are the resistivity index and the cementation and saturation exponents, or MN exponents in short. So these are based on the fluid distributions resulting from a primary drainage computation. Based on the material phase conductivities, the formation resistivity factor may be computed as well. GeoDict offers solvers for prediction of the overall mechanical properties such as bulk and shear moduli. And empowered by the field math solver of the Fraunhofer Institute, you may also compute rock deformation, even with failure, and obtain the resulting strain stress curves. In the framework of CCS, so carbon capture and storage, GeoDict's pore-scale reactive flow capabilities are facing a further increasing relevance for the industry. With GeoDict you may compute chemical transport in aqueous solutions. You may trigger local disequilibria and dissolve or precipitate mineral phases upon continuous injection of reactants. And as a result you may analyze and visualize in 4D the alteration of your digital rocks. Although CO2 injection is in its infancy, you may set up systems for CO2 sequestration based either on internal company knowledge or on available geochemical databases. Okay, let's continue with a closer look at the new features for digital core analysis in GeoDict 2023. There's plenty of topics on the DRP list, so the schedule time will allow to go into minor details. First of all, in very general, our development team has invested lots of efforts to increase the number of material phases in GeoDict 2023 from 16 to 256 separate material IDs. This will become quite handy for upscaling workflows. The import GeoWall module was extended by the import of DICOM file formats, which is a very common 3D data type for medical CT data. We have also implemented the popular random forest method for AI segmentation. This one is very similar to our boosted trees method. It's just that the random forest is slightly more robust and the boosted trees a little more efficient. Speaking of which, the latter has gained an optimization towards memory requirements. And on top, we've improved the overall performance of the UNet method, the deep learning variant, by up to a factor of 10. In collaboration with Visvasanti Chandra from the Anpark Institute at KAUST University, We are investigating the potential of a deep learning-based image enhancement feature with the ultimate goal to reliably reduce scanning times that are required in core labs. So accordingly, this study is about one of the bottlenecks of digital core analysis, which is the time that's required for image scans. I will go through our workflow, starting at image acquisition. So we need pairs of low quality and high quality scans of the same samples acquired at short and long exposure times. We use these pairs of digital images from similar formations to train a neural network. And finally, we apply the trained model to low quality scans in order to reconstruct high quality images. You can also see this with more detail from a low quality image here onto the reconstructed high quality image there. So we reduce the noise and increase the contrast as available from the high quality image. Our goal is to reliably enhance the image quality and thus reduce the imaging time by up to 90%. And we are in midst of ongoing validation work for this study, so please expect more details in the near future. With the Krylov method, we have significantly improved the LIR solver performance of flow computations in low permeable rocks. Okay, let's have a closer look. We generated sandstones with similar grain size distributions at different porosity values to test our flow solver performance with and without the Krylov method. So this plot here shows the runtime versus the sandstone porosity. The gray curve here is without Krylov and the red curve, flat one, with the Krylov method. So the results are clear. We have improved the flow solver performance in low porosity rocks or low permeable rocks by a factor of 50 and even more. In GeoDict, we have now implemented the often requested single-phase Darcy solver, available with a recording license. We have now two major solver choices for digital core analysis, which is the Stokes-Brinkman solver that's well suited for rocks with resolved pore throats, and even more with the addition of the Krylov method, and the Darcy solver, which is the method of choice in case of whole core scans, or just whenever you haven't got any flow paths resolved in flow direction. To give you a visual idea, we have applied different permeability values to gray values in a certain range. So each data point here corresponds to a gray value with a defined permeability. So for each of these intermediate gray values, we have applied a permeability in order to compute the absolute permeability in this whole core structure. You can see on the right hand side the velocities that we've computed increasing from blue to red color. And we have run the setup with both methods. The permeability results are the same within the given accuracy, but clearly the Darcy solver is by far more efficient for this kind of setup, so it's favorable a lot. In other words, we have enabled whole core computations for absolute permeability prediction. Okay, let's go into more detail here. So with the Darcy solver for whole core scans, GeoDict may now compute the absolute permeability in the entire range of core analysis scales, from nanometer resolution up to the whole core scale resolution. This enables upscaling workflows for an improved understanding of challenging formations or for comparisons to corresponding lab data. And also hot off the press, the LIR solver is now available for the prediction of the overall mechanical properties, with a quite familiar solver user interface, as you can see here, which is quite similar to GeoDict. We have redesigned the GeoDict user interface towards mixed readability setups. So if you now set contact angles for the invading fluid, both below and above 90 degrees, you will get an automatic application of both the spontaneous and the forced parts of drainage and inhibition. So that's required to consider mixed readability. Okay, let's follow this animation here of an imbibition. Water invades a sandstone with a water wet layer in the center and all wet layers at top and bottom. So clearly we see a very different behaviors in these different layers. With the SATODIC performance increasing in recent GeoDict versions, we decided to add an option for parallelization of drainage and imbibition computations. Also available, the calculation of the tumor fit is now part of SATODIC in GeoDict 2023. So if you ever encountered a mismatch between experimental and digital MICP results, as we have obtained here, it might have looked exactly like this mismatch here on the left that was obtained for a Gildehausen sandstone. The issue is just the difference in the available or seen porosity of both methods. So there's some unresolved porosity. And GeoDict 2023 will pretty much simplify your work and calculate this unresolved porosity via tumor fit, so that your DRP results may match corresponding lab data much more easily. For GeoDict 2023, we have improved the export of surface meshes in the Mesh Geo module. As shown in this example, grain surfaces are much smoother, with the number of meshes being significantly reduced. So you can see artifacts like this one are smoothed out. So this simplifies any export to other software such as COMSOL. In the GeoApp menu, the Digital Rock Physics section has obtained more apps from other modules, distributed in subsections. With GeoDict 2023, you will now find all the relevant GeoApps for digital physics in this particular section. There's one completely new GeoApp, the Digital Routine Core Analysis. This app bundles various features for geometrical characterization as well as a Stokes computation for all flow directions. For a smart overview, the results are combined with an automated generation of a PowerPoint report summarizing all the results and visualizations in one file. The MICP GeoApp now also computes the pore throat size distribution via application of the Washburn equation. So the image here shows a sample result for 500 cubic Doddington sandstone. The GeoApp Hysteresis for oil water setups replaces the forced imbibition GeoApp. This app bundles the most important options and includes a choice for rock wettability. As a side note, the relative permeability runtime, including primary drainage and imbibition for a large domain of 1500 cubic, was only 5 days, compared to several months of lab time. In GeoDict 2023, the Trapping Curve GeoApp now also features a wettability choice. And finally, we have improved the user interface and performance of the reactive flow GeoApps, while keeping an eye on the recent developments with respect to carbon capture and storage. Speaking of which, reactions, meaning mineral precipitation and dissolution, may alter the pore space, and with this, the transport properties of reservoir rocks. And since reactions triggered by CO2 injection are expected to occur in the range of years, digital approaches might be the best chance to obtain reservoir development insights in a shorter period of time. For industrial settings of CO2 sequestration, the development of transport properties and the corresponding assets, a carbon dioxide injection is one of the major questions and needs to be tackled for each fluid rock system or reservoir separately. And GeoDict offers tools to tackle these questions, even for different brine CO2 saturation states. So in other words, you may compute and combine both residual trapping and mineral trapping by using the GeoDict software package for digital rock physics. Thank you for your attention.